Just finishing off the section here. Mars has two moons. Their names are Phobos and Deimos, in case you didn't know that. They're actually really small moons. If you looked at them, they're not even really shaped like a moon. They look more like asteroids, really. They're really small. The smaller one, even smaller than the other one, is called Deimos. I wrote that it isn't quite spherical, but like I said, it looks more like a lump. Really, that's what it looks like. We can model it like a sphere, though, with a radius of 6.3 kilometers and has a mass of 1.8 times 10 to the 15th kilograms. Okay. At what speed would a projectile move in a very low orbit around Deimos? So,
what are we talking about, like very low orbit?
Ground skimming, basically.
Oh,
Okay. So we have a formula for a ground skimming orbit that we learned.
GM over radius 2.
Yeah, radius squared. So
Gravity constant.
That's the big GM, isn't it?
we have, this color. It's not a good color. So we have G, so the gravity of Deimos equals the gravitational constant, so capital G, and then the big mass, because it's a planet, and this is the mass of Deimos, divided by big R squared, and so this is the radius of Deimos. We use big M and big R for big things. Okay?
That makes sense.
So we know the gravitational constant. What was it?
6
point something.
6.67 times 10
times 10 to the negative 11th. The units are
newtons.
Is that gonna right?
Meters per seconds.
Okay.
Divided by kilograms. Or meters per second squared divided by kilograms squared.
Meters squared per kilogram squared. All right. And then the mass of Deimos, they gave it to us in kilometers. So we're going to say, the mass, they gave it to us in kilograms. So it's 1.8 times 10 to the 15th kilograms. And then the radius, they gave it to us in kilometers. So we're going to turn that into meters. So move the decimal 3 places. So it will be what?
630,000.
No.
What?
Just move it 3 places.
Oh, 3?
So 6,300 meters.
Squared.
Okay. And we got to, square it. And so then we just calculate that. 0.003. What are the units?
Meters are gone.
One of the meters is gone. One of them stays.
Meters, you still have newtons and kilograms. So you got kilograms to the third.
I do?
Well, because you got. Oh wait, no.
Remember, newtons here is really kilograms, meters per second squared, right?
Yes, we have
So
meters.
one of the kilograms on top with the newtons divided by one of the kilograms on the bottom is gone. But then this kilograms over here
is on top and
is
the other
gone
one is on bottom.
With the kilograms on the bottom. Okay, so the kilograms are all gone. The meters squared on the bottom with the meters squared on the top is gone. But the meters that was here with the newtons is still around. So the meters is still around.
Second squared.
The second squared is still there. So it's per second squared. So meters per second squared. We're calculating gravity. That's an acceleration. So the units make sense. All right. So the gravity on Deimos is a very, very small 0.003. right? And it should be because Deimos is not very big. I mean, the radius is only 6,300 meters. It's a small moon, okay? So that's not what we're trying to calculate, though. We're trying to calculate the speed the projectile needs to go for this very low orbit. So we need a formula for that, and we have it. What was that formula?
That's not VC, is it?
No, that was for like going through the loop VC.
Oh, yeah, the upside down.
Yeah. So we talked about it. The velocity for this orbit wound up being the square root of just GR. So the G that we just calculated was 0.003 meters per second squared. Use your calculator's answer though, and then times the radius of Deimos, which they again gave us, which was 6,300 meters. And this is all being square rooted. What do we get? 4.37. With significant figures here, though, we're going to call that 4.4 meters per second. 4.4 meters per second in miles per hour, double it and add a little. We're talking about just like 15 miles per hour.
Could run.
Yeah. You could actually put yourself in orbit pretty easily. Take a running jump and you're in orbit around Deimos. It's actually pretty realistic. So Deimos is not a very big moon. All right. So we got one more thing to do here, and we're done with the section. Rank in order from largest to smallest the free fall accelerations on the surfaces of the following planets. So this is a conceptual problem. Maybe you think about it, or maybe you use some formula. But I want to think about this for a second, and then we're going to come back and come up with the answer. The best thing to do on this one is, if you can't conceptualize this, think about this formula. Gravitational constant, mass over r squared. Basically what we're just doing, right? Now, the gravitational constant is the gravitational constant. It doesn't matter the size or the mass of the planet, okay? So I don't even want to really look at it. It's not that it's not there. It's just that it's not going to have any impact on anything here, okay? What is going to have an impact is changing the mass and changing the radius, right? So if you look at this equation, if the mass doubles, which is what we're doing here, we're either having a normal mass or we're doubling the mass, right? What happens to the gravitational pull?
Goes up.
It goes up, it doubles, right?
Yeah.
If the radius doubles, then what happens to the gravitational pull?
It's halves.
No.
It doesn't have.
No, it
Of course.
exponentially decreases.
Well, because of the square here, it actually will reduce by 1/4. Okay, that's the key. So now we can look at this and notice that we have A and B kind of grouped together because they have the same radius, and C and D kind of grouped together because they have the same radius, right? So let's just compare for a second A and B. They have the same radius. Between A and B, I increase the mass. So B has to have what compared to A? A bigger
Well, it's going to have bigger
gravitational pull, right? So B must be greater than A, right? B greater than A. Okay, now let's take a look at C and D because they have the same radius. So D increases the mass compared to C, right? So what must be true about D compared to C? Yeah, D is greater than C. Okay, we got that sorted out. So now the only question is, how do these two groups compare with increasing the radius? Okay, now we're going to do that by looking at this formula. Okay, so obviously, if the mass doesn't change, when I increase the radius, the gravitational pull is going to decrease, right? So the question is, what happens if I increase the mass also? So what I will do is I'm going to take this formula, m over r squared, but I'm going to increase the radius. And when I do that, I double the radius, but then that has to be squared. Okay? What do I get when I have 2r and it's being squared? What's the result?
4.
It's 4r. Okay, so this becomes m over 4r squared. We have 1/4 of the original gravitational pull, right? Well, what happens now if so that's this guy, basically, that's C, right? 1/4 of the original gravitational pull. What happens in the case of D, where I had 2 times the mass and 2 times of the radius?
Sends down 1/2.
We now have 2 times the mass over 4r squared in the end. And that would reduce to just 1/2. So we have 1/2 of the original gravitational pull, which is actually less than A. In A, we have this situation right here, which is 1 original gravitational pull. So C is actually less than A, and D is definitely less than A. And we know that B is already greater than A. So now we can put everything in order. We wind up with B is greater than A, and we know that A is greater than both C and D. So we go D and C, and that's our answer. So you use the formula, and because of this square on the bottom, this happens and this happens, and it is really important that you understand that the radius actually has a massive impact on the gravitational pull of the planet. Okay? Yeah, it is interesting, I think. All right, so that's the end of the section now. It's a bummer that we had to put it in 2 parts, but that's how it works. So there we're done.